Hi, everyone. It's Mr. Neighbor, and we're going to talk about 15.2 today, which is characteristics of waves. The first two characteristics we're going to talk about are frequency and period. Frequency is referring to how many times a wave passes and repeats itself per second. It's measured in a label we call Hertz, Hz. Period is the amount of time it takes for one wave to pass. That's measured in seconds because it's a time. So notice how these are related. Both deal with waves and both deal with time. The frequency deals with how many waves in one amount of time. Period deals with how much time is one wave. So when you look at frequency, comparing the number of waves per 1 second, dividing waves by time, that should be the same thing as 1 over the period. If we look at the period, that's how much time passes per number of waves. That should be 1 over the frequency. So if you know period, you know frequency. If you know frequency, you know period. So let's try a few examples here. Strong winds can apply a significant enough force to tall skyscrapers to set them into a back and forth motion. The amplitudes of these motions are greater at the higher floors and barely observable for lower floors. It is said that one can even observe the vibrational motion of the Sears Tower in Chicago on windy days. As the Sears Tower vibrates back and forth, it makes about 8.6 vibrations in 60 seconds. Determine the frequency and the period of the vibrations of the Sears Tower. All right, let's look at frequency first. Frequency is the number of waves per 1 second or time. So here we have vibrations in 60 seconds. So in order to get it how many per 1 second, we're going to take the vibrations divided by 60. That will give us out 8.6 divided by 60 seconds, which is 0.14 hertz approximately. Next, we'll do the period. So period, we're going to take our time divided by how many vibrations. So one vibration takes how long? So 60 seconds divided by 8.6. When we calculate that out, it'll be 6.98 approximately, which significant figures leaves us at 7. So what you should try is do 1 over the frequency and see if you get out 7 seconds. You should. Take 1 over the period. You should get out 0.14 hertz. So you understand how they're related. You can calculate it without them. All right, next problem. The spin rate of a CD-ROM varies according to the location on the disk from where data is being accessed. When accessing data from the inner circles of the disk, the CD can spin at a rate as high as 400 revolutions per minute. Determine the frequency and the period in seconds of the spinning CD. So first, we need to make sure we do things in seconds. So first, let's figure out 400 revolutions per minute. That's really 400 revolutions per 60 seconds. So let's be clear about that. Now, frequency, that is telling us how many revolutions are happening every 1 second. So I need to take my revolutions divided by my time so that my denominator eventually comes out to be 1. I calculated that, it's 6.6 repeating, which will be 7 in significant figures, so 7 hertz is my answer. Notice 7 divided by 1 is still 7. That tells me 7 rotations every 1 second. So now let's do the period. So period, capital T for that. We look at how much time passes for every 1 revolution. So we need our denominator to be 0 now. So 60 divided by 400, or you could have done 1 divided by 7, because remember, we can take 1 divided by the frequency. So 1 divided by 7 would be another way to do this problem. I get out 0.15 seconds. With SigFig, 0.2 seconds. If I did 1 divided by the frequency, I get out 0.14 seconds. So a little bit different just because of rounding issues over here. If I would have done 1 divided by 6.6, I probably would have got closer to the 0.15 that I wished. All right, next characteristic of waves. Let's talk about wave speed. Depending on the information given, you can calculate the speed of a wave to different waves. You can talk about the wavelength divided by the period, or you can do frequency times the wavelength. Now, let's just look at why you can do this, why you have 2 different waves, or waves. I'm going to get those mixed up a lot. So if I look at frequency, remember on the previous slides, we looked at frequency as 1 over the period. So let me cross this out and write 1 over capital T period. If I simplify this, lambda, which we use to represent wavelength, that is going to be multiplied to the numerator. So lambda is going to be on top, period is going to be on bottom. Notice we get out lambda divided by period. Wavelength divided by period. So these two, they're synonymous. If you want to use multiplication, you can use the frequency version, frequency times wavelength. If you want to do division, you can do wavelength divided by the period. If you only have the period, I would say do the one with the period. If you have frequency only, do the one with frequency. But they're very versatile. So use those when calculating wavelength, wave speed. So let's try some examples. All right, microbats use echolocation to navigate and hunt. They emit pulses of high-frequency sound waves which reflect off obstacles and objects in their surroundings. By detecting the time delay between the emitted pulse and the return of the reflected pulse, a bat can determine the location of the object. Determine the time delay between sending of a pulse and the return of its reflection from an object located 12.5 meters away. Approximate the speed of the sound wave as 345 meters per second. So the speed of sound is 345 meters per second. All right, let's think about what we all have. We know that wave speed is wavelength divided by period, or wavelength times frequency. So what I know is the speed. I know the wave speed is the speed of sound, which is 345 meters per second. So I don't need to worry about calculating that. I'm actually looking for either the wavelength, the period, or the frequency. I need to figure out which one. We know that the object is located 12.5 meters away. So we can assume that that is the wave length, 12.5 meters. So now, do we want to calculate period or frequency? So it asks us to determine the time delay between sending of a pulse and the return of its reflection from an object. So which thing is a time thing, a label with time, period or frequency? That would be period. So we are going to be looking for the period. So I will move these things around, move the 345 to the T spot, T up to this spot, because I'm multiplying those over and dividing them over. So I'll have T equals 12.5 meters divided by 345 meters per second. Our labels will cancel out and give us an answer of seconds. And our answer is 0.0362 seconds. A little bit more than a tenth of a second. A hundredth of a second. Very, very quickly for that sound to come back and return, telling the bat where its object is, which it should be pretty fast in order for them to not hit the object going at the speeds that they're going. Bats move very, very rapidly, and you see them take a lot of quick turns. So that needs to happen very, very them. We have a few more problems with wave speed, wavelength, period, and frequency, and we'll save that for the next video.